In the last few lectures, we showed that the global mean temperature is a function of the incoming solar radiation, the amount of radiation reflected by the Earth to space called albedo, the amount of solar radiation absorbed by the Earth, solar absorptivity, and the emissivity of the atmosphere and Earth in the infrared. We also saw that if we change any of these parameters one at a time, changes of the order of 1 degree centigrade take place. Although this is very useful to understand, one must realize that in the real world things change together. For example, when you change the incoming solar radiation, let us say it increases, so the temperature goes up. If the temperature goes up, ice will start melting, so albedo will change. So these are called feedbacks. You can think of them as chain reactions. Something changes, it sets up a reaction to for something else to change. So it is important to take into account these chain reactions, because the ultimate change in the climate of the Earth depends not only on the initial perturbation or disturbance that has occurred, how other things in the system change to increase or decrease the Earth's temperature. Okay. So this is an important issue, and this has bothered climate scientists for a long time. The reason is here. If you look at many climate models developed all over the world, okay, here we have 12 of them, and in each one of them you allow carbon dioxide to be doubled from, let us say, 280 ppm to 560 ppm, and then see what is the temperature change of the Earth. You find that some models like IAP show a value as low as 1.7 degrees, while a model like LMD here gives a value as high as 5 degrees. Now, if the actual change is around 1.75, we may say it is something we can adjust to or adapt to. If it is 5 degrees, it will be a catastrophic change, because most of the ice in the polar region will melt. Okay? So we need to know which is correct. Now, why is there so much difference between different models? This we will discuss in great detail, and I will give you a hint. The biggest problem in these models is in the way they model clouds. As I pointed out earlier, clouds have a spatial scale over the order of a kilometer, and most of these models have a grid size of 50 by 50 kilometers, which means they really cannot simulate changes in cloud accurately, because the scale of the cloud is smaller than the scale of the grid. So what is happening within that 50 by 50 kilometer grid cannot be determined from first principles in physics. So most models use an empirical technique to predict what kind of clouds will occur within the grid. Okay? This is called parameterization, and we will discuss that in some detail later in the course. So the question is, if cloud is one of the reasons why it differing so much, are there other causes? For example, in some model the ice may melt less than some other model, or in some models the vertical profile of temperature may change differently than other models. The third important factor is water vapor. The amount of water vapor in the atmosphere may not change equally in all the models. So we need to know which are the factors which are different among models, which we can trust, and which show a large difference. Okay, that is the purpose of feedback analysis. Now, the reason why it is so important is a 1% change in Earth's planetary albedo, okay, exerts as much impact as doubling of CO2. If you double CO2 in the Earth's system and the albedo changes, let us say reduces by 1%, it can completely compensate for the change in CO2. Okay. So, many people earlier thought that doubling of CO2 may not be too serious because the earth will adjust itself. This is called homeostasis. Like your body temperature remains constant whether you exercise or you sit down or you sleep. They thought earth may have a way to control its temperature, so that whenever we make some changes, some other change will occur to compensate. Now, today we know that that is not happening. Earth's climate is not stable as people thought it could be, and can change a lot, and it can change rapidly. Now, the reason why albedo change is a very important issue is because both clouds and cryosphere, that is ice and snow, can have a large impact on Earth's albedo. So, in order to understand the role of feedbacks, IPCC has defined a term called feedback and a term called forcing. It is important for you to understand the difference, and one example is the increase in carbon dioxide in the Earth's atmosphere in the last 150 years. This is not a natural change. This change occurred because we human beings drilled deep into the earth and took out coal, oil and gas and burnt it. Okay. So, this is not a part of the natural earth system. Before we did that, the earth's atmosphere was quite in a stable equilibrium, where the amount of carbon dioxide did not change much, because between the carbon dioxide coming out of the volcanoes and carbon dioxide removed by photosynthesis and dissolving in the ocean, it was in perfect equilibrium. So, the carbon dioxide amount remained fairly constant for the last 10,000 years at 280 ppm until we started burning coal, oil and gas, then it started increasing. So, this we consider to be forcing because this is external to the system, and this will disturb the equilibrium of the system. Okay. We can also consider a major volcanic eruption as a forcing. Okay. Now, as you will see, the definition of forcing is not unique. It can somewhat change from situation to situation. Okay. Now, what is a feedback? Feedback is the response of the earth system to the forcing. So, we increase CO2 by burning oil, coal and gas, and so temperature of the atmosphere went up. When it goes up, the amount of water vapor increases, the clouds change, ice starts melting. All these are feedbacks because they respond to the temperature change. They are not forcing because they are not induced externally, but they are caused by change of the temperature within the system. Okay. That is the difference between feedback and forcing. So, to make it very clear, we talk about radiative forcing, because the entire discussion in climate change science is in terms of how much radiative imbalance is caused by any perturbation, whether it is due to carbon dioxide or volcano or solar. Ultimately, they affect the top of the atmosphere radiation budget. Okay. And so, that is the radiative forcing, and it has to be external. External means something which changes without being influenced by the system. The system is earth and its temperature. Okay. So, without earth's temperature changing, if either solar, volcanic or human induced changes causes the imbalance at the top of the atmosphere, that is a forcing. Feedback is a response of the system to the external perturbation, okay, that leads to more perturbation. The examples are water vapor increasing due to increase in temperature, clouds changing can either increase or decrease due to temperature change, or ice melting due to increase in temperature. So, the key point is feedback is caused by a change in temperature. Well, the external forcing is caused by many factors which are not related to temperature. So, I will just remind you again, radiative forcing is a concept used in climate science to quantify the change in the energy balance at the top of the atmosphere. Okay. Now, there are three types of radiative forcing that is mentioned in IPCC. The first one is called instantaneous. That is, as soon as the change occurs, let us say change in input solar radiation or a volcanic eruption, we take the change into account. We do not account for the immediate change that occurs in the stratosphere. Stratosphere is the region above 15 kilometers in the Earth's atmosphere, in which temperature goes up. In the troposphere, temperature decreases height. We will discuss that little detail later. Now, stratosphere is much thinner than troposphere, because all of you know that the density of the atmosphere decreases height. As you go higher in the atmosphere, less atmosphere, less mass. So, stratosphere has little mass. So, as soon as you do any forcing, it will immediately change. So, earlier people did not account for the change in stratospheric temperature. Later people felt that because it changes so quickly, we should adjust the radiative forcing in response to change in the stratosphere alone. So, they did not change the tropospheric properties because they take time to change, and they allowed stratosphere to adjust to this forcing, and then calculated the radiative imbalance. Now, recently IPCC has changed its thing further, and they call that another term called effective radiative forcing, where they allow both stratosphere and troposphere to change. Okay. Now, these three things do not alter the forcing substantially, they do make some change, and the reason why this has been brought in, because in the future, when there will be very strict laws about how much carbon dioxide or methane a country can emit, everything will be defined in terms of radiative forcing. And so, now the accepted radiative forcing standard is effective radiative forcing, that is allowing stratosphere and troposphere to adjust, because these will adjust within a few days. Because although troposphere is much higher mass than stratosphere, it is still of a much lower mass than the ocean. The ocean is one which changes very slowly over years, decades and centuries, and that is what we should be worried about, not change occurring within a few days. So, the IPCC now uses effective radiative forcing as a concept, but I can tell you that the differences between these three is not much. Okay. From our purposes, in this first course, we will not distinguish too much from these three, but if you are going to read literature and research papers, you must be aware of this difference in the way radiative forcing defined at the top of the atmosphere. Now, here is an example of radiative forcing as given in IPCC for the change between 1750 to 2005. Okay. And this is presented to tell people that if you look at the total net human activities affecting the radiative forcing, it is around 1.6 between 1750 and 2005, and out of which the most important one is carbon dioxide. That is why there are negotiations going on how to control the carbon dioxide emission on Earth, because this is a dominant component. Secondly, carbon dioxide has a long lifetime. It remains in the atmosphere for hundreds of years. So, if you do not make changes now, it will impact the Earth's climate for hundreds of years. The next important gas, greenhouse gas, are methane, nitrous oxide and so called halocarbons, like freons used in refrigerators. Okay. These are chlorine, fluorine and carbon compounds which are used in many devices like air conditioners, refrigerators and so on, and they were thought to be harmless 60 years ago because they are not toxic, they do not easily catch fire and so on. But it turns out that these are bad for two reasons. One, they go to Antarctica and destroy the ozone layer in the stratosphere, and they also cause greenhouse effect. So, these are minor gases. These are, if carbon dioxide concentration today is 420 parts per million, these are much smaller. Methane is in parts per billion, and some of the halocarbons are in parts per trillion. Although they are very small quantity, they still have an impact, and we will discuss why it is so. Okay. I mentioned briefly that some of these gases absorb radiation in the region between 10 to 12 micron, where neither water vapor nor carbon dioxide absorbs radiation, and so they have an impact. Okay. Now, in addition, of course, ozone is changing. It is reducing in the stratosphere and increasing in the troposphere. So, in the troposphere it will cause further warming, stratosphere is called cooling. So, all these are accounted for. Then we have to account for aerosol, that is small particles which we release in the atmosphere due to industrial activities like soot, which causes warming. If you deforest a piece of land, it will change the albedo of the earth. Also, in the atmosphere there is a direct impact of aerosols which reflect or absorb radiation, or they have an indirect effect by changing the cloud albedo. So, I want you to notice that if you add the greenhouse effect of carbon dioxide, which is 1.7 here, and other small gases is 2.7, half of it is counteracted by aerosol. Okay. So, if you take this and this, you are getting around 1.6, and I want to notice that impact of changes in solar input is very, very small. Okay. There is a small effect due to the 11-year solar cycle, but it is very, very small compared to human impacts. One also is worried about the impact of aircraft going around in the stratosphere, but that impact is still quite small. Okay. So, this table or figure from IPCC gives you a clear indication that if you want to control Earth's climate, we should be focusing mainly on carbon dioxide and methane. Okay. Those are the two major gases of concern. Carbon dioxide has a long lifetime, so it has to be done quickly, otherwise it will continue to affect. Methane has a lifetime of about 10 years. So, methane, if you release today, in 10 years time it will become carbon dioxide and water vapor, and its impact will not be that much. So, but still methane is a very powerful greenhouse gas, so we have to try to control it. Now, there is another figure generated for a more recent period, and here they use effective radiative force, that is, they account for changes occurring in troposphere and stratosphere on a short time scale, and you can see that numbers are slightly different, not very different, and ultimately you are getting a number like 2.246, 2.7 watts per meter square net effect. Okay. And but that is because we have gone from 2000 to 2019, and so you are getting a value of 2.72, but I want you to notice a large uncertainty in this radiative forcing. 2.72 is the mean value, but the range goes from 1.96 to 3.48, and the high uncertainty is mainly due to aerosols. Aerosols have a large uncertainty because we do not have a good data on its variation in space and time, and also they affect clouds in ways we do not fully understand. So, aerosols have a huge uncertainty in their cooling of the order of 1 watt per meter squared, and that leads to this large uncertainty of around 1.5 watts a meter squared. So, this is something which we have to accept until better measurements are made about aerosol and their impact. Okay. So, this is the most recent data from IPCC. Now, some of you may not like the term radiative forcing because in watts per meter squared, it may not give you a feel for how much temperature change is occurring. Okay. So, IPCC also provides how each of these molecules have an impact on temperature. This is without feedback. And so carbon dioxide itself, its change in the last 150 years are around 0.75, methane is around 0.5, others are much smaller. Sulfur dioxide, an aerosol, sulfate aerosol, causes a cooling of 0.5. So here they are not included for aerosol and clouds, and so they are showing clearly that in terms of global temperature change, the dominant effects are CO2, methane and sulfur dioxide. So these are the ones, and of them sulfur dioxide causes large uncertainty in our estimate. Now we come to the definition of climate feedback. We look at temperature change global mean on the earth. We look at Q as a forcing, which is independent of temperature, and the feedback which depends on temperature. Okay. Forcing can be incoming radiation called insolation or carbon dioxide emitted by human beings or by volcanoes, and feedbacks are those quantities which depend on temperature like water vapor, clouds, ocean circulation, all these change when temperature changes. Now, so the distinction between forcing and feedback is quite clear here, but there are cases where it is not so clear. Take methane. Methane in the atmosphere is a forcing if we consider methane emission by rice fields. As human beings increase their population, more and more area of the earth is covered with rice fields, and rice fields emit methane. This is a forcing because this is something human beings are doing on a large scale. Okay. On the other hand, as the temperature of the earth increases, there are regions in the polar regions where there is frozen soil called permafrost. These start, when temperature goes up, these start melting and methane comes out. Okay, we will mention this later in the course. And this methane now is a feedback, because this methane is coming out not because of any forcing, but because temperature of the polar region is changing rapidly. So methane is both could be a forcing as well as feedback. So it's a little complicated quantity, but most other quantities one can clearly distinguish between forcing and feedback. Now let's go back to the radiation, net radiation at the top of the atmosphere, which is the focus of our simple climate model. So incoming radiation, and this is the absorbed 1 minus albedo, this is the outgoing long wave radiation. Okay. So net radiation can change, either you see sun's input changes or Earth's albedo changes or OLR changes. Okay. So changes in albedo or OLR can be on account of either forcing or feedback. Forcing is of albedo changes, for example, deforestation. Human beings over the last 10,000 years have converted a large amount of forest into agricultural land, they change the albedo of the earth. Okay? That is a forcing, which is not natural. Okay? Now, if human beings have released CO2 in the atmosphere by using fossil fuels, that will affect OLR, that is a forcing. Okay? But OLR can also change due to increase in water vapor, which is caused by temperature change, that is a feedback. Okay? Similarly, albedo can change due to melting of ice because temperature goes up, that is a feedback. Okay? So human deforestation is a forcing, global warming causing ice to melt is a feedback, human induced increase in greenhouse gases like CO2 reduces OLR, that is a forcing, and increase in water vapor due to global warming, that is a feedback, and increase in methane due to rice cultivation is a forcing, and global warming induced by methane increase due to temperature increase is a feedback. So you must understand this distinction clearly in each situation. So, now we want to understand what determines the response of the earth system to any forcing. Okay. So, how much response occurs depends on the amount of forcing and what kind of feedbacks occur in the system, which either amplify or dampen the initial forcing. Okay. So, this net radiant top of the atmosphere is altered by some forcing like increase in CO2. Once that happens, the temperature of the earth changes. Once it changes, some things will change like OLR or something else will change in response to temperature change, okay, and that will add or it will reduce the initial forcing. Okay. Ultimately, of course, system has to come to equilibrium. So, the temperature of the earth will increase or decrease such that finally the initial forcing is adjusted. Now, if there are no other feedback, there is one feedback which will always occur, is called the Planck feedback, that is the emission by the earth surface to space, which will always occur even if there is no atmosphere, and that is called the Planck feedback. That is always negative, that is earth as soon as forcing occurs, its temperature will go up such that this quantity will try to balance this quantity until it reaches 0. Okay. But there are other things which are changing which depend on temperature. So, the other things are called X parameter. It can be water vapor, it can be clouds, it can be even albedo change. If all these change due to temperature change, then these are the feedbacks. Okay. This is also feedback, this is a direct feedback that is same in all models because it responds to the temperature change, but these will differ from model to model. Okay. We will see that in both these are feedbacks. One is immediate direct feedback, one is in response to change in some variable. So, we will see the distinction very soon. I will focus first on the most important feedback, which is water vapor. Now, this was recognized more than 120 years ago by Chamberlain, who said water vapor in the atmosphere is dependent on temperature. This is from the laws of thermodynamics, which say that if the temperature of the atmosphere goes up, water vapor must increase, because there is a relationship between saturated water vapor in the atmosphere and temperature. Okay. So, temperature goes up, water vapor comes out from oceans and lakes, gets into the atmosphere. Okay. And so, water vapor is a very powerful greenhouse gas, we saw that. So, it will start trapping heat and raise temperature further. Okay. This is the most important feedback in the Earth's climate system, and it plays a very important role in the way temperature changes. To highlight that, I want to show you the change in outgoing long wave radiation as a function of Earth's temperature for a dry atmosphere and atmosphere with water vapor. Okay. In a dry atmosphere, this will change like sigma T to the power of 4, like the Stefan-Boltzmann's law, because there is no other absorption, it will go on increasing. But because as the temperature goes up, water vapor goes on increasing, the actual OLR cannot increase as rapidly as the OLR increase without the atmosphere with water vapor. So, this is a huge amount. You can see that if the temperature goes up by 100 degrees Kelvin, the water vapor feedback can give you typically 150 watt per meter squared difference. We saw that earlier also. So, this is a very important feedback which must be understood. Now, the whole advantage of feedback as a concept that IPCC likes to have is because of the belief that the feedback parameter is useful because it is independent of the type of the forcing. Whether increase CO2 or solar radiation or something else, the water vapor feedback will be similar. Okay. Today we know it's not strictly correct, so people have objected to that thing, but still for purposes of policy we can still say with some confidence that the feedback parameter that we develop, whether we increase CO2 or sun's radiation or something else, will be similar. Okay? The way the earth responds to any forcing is quite similar. Okay? Now, second important thing about feedback is that time scale separation between forcing and feedback. Forcing, let us say we increase CO2 today, it immediately changes the net radiation, but feedback will change more slowly. That is because the ocean, which is the one responsible for the most of the feedback, changes very slowly because it has a huge mass and has a huge thermal inertia. So changes in temperature of the ocean will not occur immediately after the forcing. It will take a few years. Okay? So the scale separation is very clear. Take methane as an example. Methane can be a forcing or a feedback. When it occurs as feedback, it occurs a little later. It won't change immediately. If we change CO2 in the Earth's atmosphere today, temperature of the permafrost will change after a couple of years. So methane will increase after a couple of years. So methane in that case is a feedback. Well, if methane is directly introduced into the atmosphere by human actions like having rice fields, that is an immediate effect. Okay? Water vapor is always a feedback because water vapor responds to temperature alone and nothing else. Now, to understand this in a simple system framework, this is a cartoon that normally is drawn. Think of the earth as a black box, a climate system. It has incoming radiation or incoming solar radiation, and the impact of this is to have temperature 15 degrees centigrade, which is the output. Okay? This is called an open system. There are no feedbacks. Now, if we introduce a feedback, let us say due to change in temperature, okay, the temperature increases, the system will change and an additional forcing will occur, okay, due to feedback. So, for example, if you double CO2 in the Earth's atmosphere suddenly, then the OLR will reduce by 4 watts per meter squared. Okay? That is the forcing. Without feedback, the temperature change at the atmosphere 1.1 degree. But because of the change in ocean temperature, water will increase in a couple of years and due to the feedback. Now, this was shown very clearly by Professor Manabe in one of his simulations, which he did almost 25 years ago. He ran 2 climate models, coupled ocean atmosphere model. In one, he kept the water vapor constant in the atmosphere. You can do it in a model, you cannot do it in the real world. In a model, you can say water vapor to be fixed at the initial value. Okay? So, as you increase CO2, you double the CO2, the temperature goes up, but whatever doesn't change. So, the temperature of the earth increases to 1 degree and remains roughly constant. Okay? But if you allow water vapor to increase air per the laws of thermodynamics, then the temperature slowly increases further and further and further due to water feedback, and it stabilizes at a value close to 3 degrees. So, in this model, the feedback has increased the global mean temperature by 2 degrees. Okay? It shows clearly that water vapor is a feedback parameter, because if we artificially keep water vapor constant in the atmosphere, which is not correct, but we do it to understand the role of feedback, the Earth's climate system had only 1 degree warming. So, this is a nice illustration of the role of feedback, which occurs slowly over a period of 100 years or so and then stabilizes. Okay? So, this is a important point in the list of Manabe, who got a Nobel Prize in 2021 for the work he did in climate models. Now, to summarize what has happened, you start with a system, okay, which is in equilibrium with 240 watts per meter squared absorbed from the sun and 240 meters squared emitted by the earth system, suddenly you increase CO2 by a factor of 2, okay, abrupt change. Then the OLR comes down to 236. Okay. Immediately temperature changes by 1.2 degrees in the first year without feedback. Okay. And the Earth's outgoing radiation becomes 240, but slowly the temperature of the Earth goes up further due to feedback from 1.2 to around 3, and over the long term again it is just 240 now, but with a higher temperature of the Earth. So this temperature of the Earth change due to forcing without feedback and with feedback, and finally remember the system comes to equilibrium after 1 year, after many years, to what is the absorbed solar radiation. So we will conclude this lecture on this note, and we will continue this in the next class.